doing something. But anyway, let's get going. Did anyone have any thoughts on the homework that they wanted to vent at me?
Homework 3?
Yeah.
Well, aside from the fact that your MATLAB code didn't work for some reason on my computer, nothing else.
So did you take
MATLAB
like
works fine for
did
me.
you take a screenshot and type it
No,
in?
no, I typed it all myself. For some reason, all I was getting was a flat horizontal line across the screen.
Huh.
I managed to do it using Excel.
That's what happened for me too. I think one of your values might have been off by a factor of 10.
It was. So the latent heat per unit volume for aluminum was off by a factor of 10, right? So when I played with it the other day, what happened was I realized that
also, apparently, it is really. I'm succeeded, but it is really, really hard to find interfacial energy values online.
So lots of people are saying they did. I simple Google searches.
Yeah, I got at least 3 or 4 emails last night trying to find the interfacial energy values, and when I typed it in to Google, it was the first result that came up that gave me what I needed.
Right.
So I'm not saying
I typed into Google and that did not happen for me. For some reason, like for both air and water, it wasn't giving me the values from straight Google. So
I eventually used image, something like that. It wasn't Google.
Right. So just interface energy, water, ice, water, interfacial energy, right? Surface energy on freezing temperature of water. So solid liquid interface, right? So I mean, I basically tried them all out by just doing really simple searches. So the ice air one, I actually had a couple references for. Right, so this paper here, which we have access through the library, actually just has them all out in a table that's older. Interfacial energy of ice water databases. Anyway, the point is, that's a skill finding these sorts of things is a skill that I'm trying to engender.
And it will be one that will serve you very, very well. I see a bunch of things in the chat about people frustrated that they had to use research papers to find the values, but that is something that will never, ever, ever leave you. You will always need to find literature values for your experiments later in life. And so I know it might be frustrating now, but it really is a very, very important skill to learn.
Right. So, I mean, I'm also going to be preachy for a second, right? And, you know, you guys did have 2.5 weeks for the homework too, right? So, last night was probably not the time to begin looking for them. So I get everyone. I see all the messages in the chat. I get you. I hear you. But we'll just say I do, you know, I wanted you guys to look them up for a reason, right? And that's because I want everyone to sort of develop the skill of looking through these. Right. So the other thing is, I want also keep reiterating this, especially in office hours and things like that. At the end of the day, I really don't care about your final numerical answer. I care about your logic and thought process, right? So you could actually do that problem without the values, right? And just say that, you know, we know from the reading that this is the general trend of these energies. And if you go through that, if we have heterogeneous nucleation, right, meaning that the contact angle between the ice and liquid water is less than 90, right? It's going to be this situation, and then in order to wet it, this has to be the difference in interfacial energy. You know, that would have still been like 95% of all the credit. So don't, you know, we'll chalk this up to a lesson on both sides. Right. You know, I'm hearing your feedback. I'm going to adjust future homework assignments, but these are still important skills that I want you guys to have. So the other grades are coming. Solutions are going to be posted this weekend. So you'll have homework solutions, complete homework solutions for the first 3. Thanks, Joel. You'll have the homework solutions for the first 3 this weekend, so that you can use that to prepare for the exam, and then over the next week or so, we'll be getting homework grades back. It takes a long time to do the homework, but it also takes a long time to grade it. So there'll be rubrics are going up for the homework, so you'll see exactly how they are graded, right? And essentially, really, the main thing that I'm looking at is the logic of the problem, right? Just showing me that you understand what the relative physics are of the problem, right? Again, I don't care about the final numerical answer at all, right? Generally, the same with my exams. You can get the final answer completely wrong, orders of magnitude off, and still get an A on the exams, right? So, and also, you know, keep in mind, I know it's, there's always a large curve in my classes too, so. But I will try and reflect that in all of the individual grades, right? So it doesn't look like you're going into the approaching the end of the semester with a failing grade when you actually have a B. So we'll be updating the curve for sort of for each assignment. I'll be posting the on Carmen. You'll see like your absolute, score for each of the assignments, but I'll make it clear what the class average is and what the points, what the likely, right? So if you see that I did about the average, well, the average is going to be around a B, right? So, don't be panic if you see that you got a 60% on the homework, right? That could very well be an A, depending on how everything shakes out. Okay, so let's talk a little bit about diffusion. This is going to go pretty quickly compared to the other, the previous subjects. But diffusion is, this is really central to anything to do with solid state processing, right? Because anytime we're dealing with materials in their solid state, diffusion is really the only form for mass transport, right? And sometimes we want diffusion and sometimes we don't, right? Oxide dispersion strength in steels, ODS, work because we have secondary phase particles that have exceptionally low solubility of those elements in iron, so that there is no particle coarsening through diffusion, right? Other times, if we're doing a semiconductor interface, right, we need a nice clean junction. So we don't want diffusion between two different oxide species, say, right? Other times we might want diffusion, right? If we're trying to get certain phases to be present in our material, we want to enhance diffusion. So this is just a really important kind of topic, right? So why do we care? Here's a really simple example that everyone should sort of be familiar with. This is just a cross section of the iron-carbon phase diagram. So if we start from liquid, we come down through the paratectic up here, that as material scientists, we normally don't really care much about because we're mostly processing things in the gamma phase or the austenite phase. But the welding engineers in the group are really have to consider, because they're doing the liquid processing and for fusion welds, really have to consider what's going on in the paratectic, but we're going to ignore that for right now. So we come down and we hold for a long time in this gamma phase field, in the austenite phase, and we're completely uniform austenite, right? Everything's nice and homogeneous. We have nice grains, and we come down through something that looks like a eutectic, but it's not really truly a eutectic, because a eutectic is defined as liquid goes to alpha plus beta, right? This is a eutectoid because we're going from one solid phase to two solid phases of different compositions, right? And in this case, the compositions are alpha, ferrite, which is BCC, gamma, this austenite's FCC. So we're going to BCC iron with a lot less carbon in it, and cementite, which is an intermetallic carbide of iron and carbon, right? And so we're going from uniform to a two-phase lamellar structure, right? And this looks like, perlite looks like a eutectic solidification, right? That we talked about before, except it's a completely solid state phase transformation. So instead of mixing in the liquid, we have diffusion in the solid, right? The cementite is 6.7%. The perlite is 7% carbon. The ferrite is 0.7, roughly 0. The austenite was 0.77 at the eutectoid composition, right? So we have to have this long range relative to the size of the carbon atoms, right? Diffusion in our material so that we can grow these two forms. So the growth of this perlite is going to be limited by how fast carbon can diffuse in the solid state, right? And what happens if we can't diffuse fast enough, right? What if we cool down too quickly? What happens, right? If we cool down at some moderate temperature, we get other phases like bainite that form, right? If we cool down too quickly, what do we get? We get martensite, right? Which is a diffusionless phase transformation. So the carbon still stays locked in, and now we have a supersaturated solution of carbon in the martensite, and we have very brittle properties. So the whole history of steelmaking and why steel is such a really important material has to do with understanding what the diffusion rate of carbon in iron is. Everything that we make out of steel directly depends on that diffusion. So let's take a really simple experiment, right? So there's a glass tube filled with water. At time equals 0, you add a little bit of ink to one side, and you measure how far the ink is gone, or the diffusion length, lambda, as a function of time, right? So, you can do this, you can look at the tape measure and do this, or you can just trust me that these are the actual values. And if we plot the diffusion length versus time, we notice that we get a decreasing length, or the diffusion length is monotonically increasing, but the rate of growth is decreasing with time. And it turns out that there's a square root law, right? And this is the most important thing. If this is all you remember about diffusion, this is all I care about, right? The diffusion length is going to be approximately the square root of dt, right? This is, d is the diffusivity, right? T is the time, and the length that a species diffuse is given by square root dt, right? This is one of my all-important rules of thumb, right? So if I think about solving any problem that involves diffusion, the first thing my brain goes to is square root dt, right? And that d has a exponential or an Arrhenius relationship with temperature, right? Because it's atomic jumps. And from that very simple physical picture, I can put a model of the system together in my head and understand physically what's going on, right? So in this case, if we look at the data, we can plug it in and we can find that our diffusivity is just some value, right? Usually given in something like centimeters squared per second, right? right? So it has to be centimeters squared. The units always confuse people because we have the relationship here, length equals square root of dt, right? So the diffusivity has to have units centimeters squared. We'll talk about these units, or centimeters squared per unit time, right? We'll talk about where these units come from and how to interpret these next week. All right, but right now I'm just trying to motivate some key ideas here. And one of the key ideas is a notion of random diffusivities controlled by a random walk, right? So if we think about substitutional elements in a mixture or an alloy or an ionic compound moving through a substance, the main mechanism is vacancy diffusion. Okay, so an atom can only move when there's a vacancy next to it, right? The exchange of two atoms, right? If one went into this one with the arrow, that's a huge energy cost for two atoms to switch, right? But an atom hopping into a vacancy, this is much less energy, right? So as a first approximation, we can say that the atom can really only move when it's next to a vacancy, right? Which means that individual atoms are not going to move very much, right? But the vacancy can move all over the place. In fact, it's much easier to visualize this vacancy moving, right? Kind of like visualizing electron holes in a semiconductor, right? So if you think about this as vacancy hops, the atom hops in, and now the vacancy has moved from this position to this position over here, right? And now what can happen? Well, now we have other atoms that can jump in, right? So what's the coordination number for FCC and HCP? Yeah, so Noah's got it. The diffusivity is flux through an area, right? But we'll definitely talk about that. Right, so what's the coordination number for FCC and HCP?
FCC is, I believe, 0.7. No, that's the APF.
That's the packing factor, right? How many
is
neighbors?
FCC is 12. BCC is 8, I think.
Yep, and HCP is also 12, right? So we have 12 neighbors that can hop in to this vacancy, right? And then the vacancy's moved, right? So there's now 12 new neighbors, but the atom that hopped into the previous vacancy position is still a neighbor. So in FCC, you have a 1 in 12 chance of the atom hopping back out, right? And an 11 in 12 chance of the vacancy moving to some other position, right? Right. So when we have atoms hopping around like this in a crystal, right? This is essentially self-diffusions, right? Atoms are exchanging their position under a zero change in chemical potential, right? So why is there a cost for this atom to hop into this vacancy? Why do we need there's an activation barrier, right? There isn't a net energy cost because for self-diffusion, this position is exactly the same as this position, right? But we have to have an energy barrier to overcome, and that's because there's some hindrance, right? These other atoms 1 and 2 need to be moved out of the way slightly. So that means we need some vibrational energy or thermal energy given by KT. Right? And that's sort of the hand-waving picture as to why the diffusivity depends on temperature. Right? And once I said KT, then you should immediately think of the Boltzmann statistics in the Arrhenius equation that we talked about for nucleation. Right? So the frequency at which these jumps occur is going to be dependent on KT in an exponential way, but also linearly proportional to how many attempts there are. Well, how many attempts do we have, which is going to be given by the vibrational frequency of these atoms. Right? Again, we'll talk about this in more detail, but that's the big picture. Right? So the rate equation looks very similar to the rate equation that we saw in the previous section. Right? So, but this is, diffusion in this situation is generally slow. Most atoms don't have a vacancy next to them. Right? So the atom will only move essentially as far as as fast as the number of vacancies that we have, right? And in the case of self-diffusion, forward jumps are just as likely as backward jumps, right? So over time, if we think about this, if this vacancy is moving through the crystal, what's my expected distance, or what's my expected position averaged over time of my vacancy? Right? I'm just as likely to go forward as backwards, or up as down, right? So averaged over a large period of time, my vacancy doesn't move, right? It has a net zero, a net zero change, right? Or the position ends up being a Gaussian shape that we'll look at in just a little bit. Interstitial diffusion, on the other hand, is much faster, right? The interstitial atoms are much smaller, right? They're sitting in between the other atoms. There's much less hindrance, but we also have a generally a completely different situation, right? In the substitutional case, an atom can only jump if there's a vacancy next to it. Generally, the concentration of substitutional atoms, of interstitial atoms, is going to be small, right? In carbon, in iron carbon, the max carbon is 0.77%. Dissolved in the ferrite, right? And so that means less than 1% of carbon atoms have a carbon atom in a neighboring interstitial site. And so that means there's lots of options where this atom can jump to, right? So interstitial diffusion is like giving the carbon atom a Porsche on the Autobahn compared to substitutional diffusion or vacancy diffusion in terms of the rate, right? So we have a couple different types of octahedral sites, interstitial sites. These are both the octahedral sites in FCC and BCC, but we also have, we also have tetrahedral interstitial sites, which are made up by these two atoms and these two atoms and these one to make a tetrahedron up here. And so there's another interstitial site, potential site up here. So in both FCC and BCC, we have to consider that there's two different places in the unit cell that the interstitial can go. That's something that's really interesting if you take a physical metallurgy class, to think about where the different interstitial atoms can go, but it's a little beyond, and what the implications of atoms being in an octahedral site versus a tetrahedral site is. But it's a little deeper than what I want to go here. So where does this square root dt come from?
I got a question.
Yeah.
To previous slide. So this is really specific to welding engineers, but if you, okay. We took our steel and we heated it up, and that pushed the carbon out.
Mm-hmm.
I'm just curious on like tempering, and I'm curious, did we actually get the carbon out, or was it just more of the surface? I mean, how like percentage of
okay, so if you're
carbon.
Yeah, so if you're tempering, right? So you've come down into martensite. The martensite is a tetragonal, slightly tetragonal unit cell, but it's close enough to BCC, right? The change from A to C is really small. So we can, without any real loss of generality, we can think about the BCC. Right, the carbon really doesn't want to be in here. Right, there's not enough room. In BCC for it, right? It's just when you quench down to martensite, there isn't time for it to diffuse away, right? When you temper, you're diffusing the carbon out of martensite, letting the tetragonal structure relax to BCC ferrite, and forming carbides, either in the form of perlite or grain boundary carbides, or you're dissolving away. You do get some decarburation at the surface, right? You do get some decarb, but it's not a huge amount relative to the concentration of the carbon in the steel, right? You can overcook it, right, and really reduce the carbon content, but that's generally damaging, right? You don't want to do that. So when you're tempering, you're getting the carbon out of your martensite and growing carbides in your material, in other places in your microstructure. Does that make sense?
Yeah, thank you.
All right. Okay. So back when I was learning this, I had a really great instructor, Michel Barsoum, I showed you the Fundamentals of Ceramics book that he wrote before, but he also had the great saying about that most people use thermodynamics like a drunk uses a lamppost, not so much for illumination, but for support. He also introduced diffusion through a drunk leaving a bar, right? So imagine you have someone who's had a few too many, and they can't exactly remember where their house is relative to the bar, and they walk out and they start stumbling through the streets, right? Is there any preference to sort of which way they're going to go? Right?
They would probably follow the street unless they're idiots and walk right across it.
Okay, so they're going to follow streets, right? So they're on some kind of lattice, right? So that's a good analogy, right? And so imagine you have 100 drunks that leave the bar all at the same time. And they all go for half an hour before they pass out. If they're moving around at random, what does their distribution in the city look like?
It would be completely random. Someone just kind of spin in circles for half an hour for passing out. Some would probably make it the full radius. Some would probably eventually go to another bar or go to their cars. Who knows?
Okay, but what do you think? Are you going to have more closer to the bar or more farther away from the bar?
Probably more further away. If they 30 minutes.
That's an interesting thought. Some are going to end up in jail. Sounds like a St. Patrick's Day party. Did you know that Scranton, Pennsylvania actually has the second largest St. Patrick's Day parade in the country, behind New York City? I didn't know that, but it turns out that, and it's always the week before St. Patrick's Day, so it's like a dress rehearsal for everyone participating in the New York City parade. They do Scranton first. I didn't know that until recently because my brother-in-law lives in Scranton. Yeah, so most end up closer to the bar, right? If they're actually stumbling about at random, they're just as likely to go forward as they are backwards. So they end up on average closer. And we'll take a quick look at some MATLAB examples. Now, imagine that the bar is in San Francisco and it's on the side of a steep hill. Which way, where are all the drunks going to end up? Right? Are they, in that case, are they just as likely to walk uphill as they are to walk downhill? Right? We've introduced a bias into our system now, right? Where you can still have backwards and forwards jumps, but now our jumps are more likely to go in one direction than another, right? So all the drunks end up at the bottom of the hill, right? And so the question now is, what is that hill? What is that actual driving force? But I want to take a quick look at doing some visualization here. So this is just a really simple random random walk code here. Well, let me. So let's just take 1,000 steps, right? So each atom here in this case starts at the origin, and it'll take 1,000 steps, either north, south, east, west at random. And we'll do 10 different runs of it, and we'll talk about what that means in just a second. But what I want to show is So you can see the output here. It's plotting one walk at a time. Right? And they're all going each walk is completely independent, right? And they take these sort of twisty turny paths, right? There isn't a straight line in here, but what we see is that even with just 10 walks, we see that we're more or less uniformly distributed around the middle. I mean, in terms of the angle, right? There is no preference for direction. And that,
So I was completely wrong in my logic. They would be closer to the bar.
and they're going to be clustered closer, right? And so, I wonder what the heck is it doing? There we go. Okay.
So what is the bar in the actual case? Like, what's the center?
Well, it's just sort of a starting point, right? So if we think about where a vacancy is at time 0, or where an interstitial atom is at time 0, right? We just call that the origin. So what I want to do is, let's do a simulation. This time I want to do, instead of 10, let me just do 10,000 random walks. This will take just a second. Okay. So what this is showing here, actually, I'll explain that in just a second. So let's take a look at just the x coordinate. Of where all the positions ended up, right? So here's the x coordinate, and right, this is just the histogram frequency, right? So what does this shape look like? What distribution does this look like to you guys?
Bell curve.
It's a bell curve, right? So this is a Gaussian distribution, right? So the distance, the position in either x or y is approximately Gaussian, centered on the origin, right? So there's a much higher frequency of finding things near where they started than farther out, right? So let's just take right, the average position is 0.07.31, right? So that's the mean position, right, of where things ended up. The actual distance, right, because remember let's take a quick look at, really? Okay, so if we look at this in the 2D, right, we see that we're pretty symmetric, right, in both x and y, right? We're clustered around our origin. Right, and so we've got this nice Gaussian curve, but if we want to consider the actual distance, right, we need to look at something else, right? What is the expected distance from the origin? Because remember, our distance formula is the square root of x squared plus y squared, right? I want to know what the distribution of actual deviation from the mean is, right? So we can calculate the distance. And take a look at the histogram. Right? And so we get something that looks like this. And you probably don't know this, but if the original X and Y are both Gaussian and independently Gaussian and jointly Gaussian, which they are, that means that the distance, the Euclidean distance, is going to have a Rayleigh distribution, right? And in this case, we get a mean that's somewhere around 20 something. So let's see, what is the mean of distance? $27.9, right? And how many steps did we do? We did 1,000 steps, right? So what's the square root of 1,000? 31. So the average distance from the center of our atom or our vacancy is going to be given by the square root of the number of steps we have, right? And so we can think about this as the number of steps are time, right? And our D is essentially the number, the length that our diffusivity can be thought of as the length that it goes per some unit time, is another way of thinking about that, right? And so this random walk, simply moving backwards or forwards, up or down at random, gives us this square root dt rule that we observed empirically from that from that simple example of water, ink in water, right? So what this plot is showing, this is the distance of the farthest atom, the square of it, right? So this is really jagged, right? So this is out of 10,000 simulations. Let's pick the simulation that has the atom that's gone the farthest away in every out of every possible simulation. So this is going to be very jagged. But if we look at the average distance, averaged over of all the atoms, averaged over all 10,000, this is really linear with time. So the squared distance is a straight line with time, right? So, and this is what we see in diffusion, and this is just coming from basic random walk probabilities. It's not hard to derive explicitly the square root dependence, right? But I don't think we necessarily need to do the math for this. It's just important that I think that you get an appreciation that it comes directly from the random walk, right? If we just envision our atoms as essentially random drunkards leaving the bar, walking along a lattice of city streets, we get the physical picture and the intuition of what's happening. So now the question is, I talked about the hill, right? where if we have a hill and the bar's on the hill, then the people are more likely to walk down the hill than up the hill, right? I will definitely put the script up on Carmen. That's fine. I can easily do that. So what is the hill? The hill is chemical potential, right? That's going to tell us which way that we want to go, that things want to go, right? So on Monday, I'll talk about chemical potential and then talk about interstitial diffusion in some detail. But it's important to realize that when we're talking about this, the driving force is not necessarily the concentration gradient, right? That's what you learned in chemistry 1, right? If you put ink in water, it diffuses in a direction that's given by the concentration gradient. Diffusion will not always happen down a concentration gradient. It's going to happen in the direction of chemical potential, right? And if we have a miscibility gap in our system, when we phase separate, we're actually diffusing atoms against the concentration gradient, but in the direction of our chemical potential gradient, right? So we have to keep in mind that in the simple examples you looked at in chemistry in 2010, the concentration gradient always told you which way things are going to diffuse based on Fick's first and second law. But when we're talking about phase transformations, you can have inverse diffusion. And you often have inverse diffusion where you have species that are moving against the direction of their concentration gradient, right? Which tells you one of the reasons why I said that chemical potential was such an important concept for us in this class. Okay? Have a good weekend, everybody. Look for the homework, detailed homework solutions will be posted. Hopefully the graded homework 1 will be up as well, right? And so enjoy yourself, and we'll talk to you all on Monday.
Can I just say I'm really glad the midterm for this class is very late, because we have a midterm this week, a midterm next week, and it's good it doesn't pile up.
Yeah, I looked at, I tried to keep that in mind. And because the day to drop is later, I felt a little more comfortable pushing the midterm back a little bit. And really more, I just want to make sure you guys have enough time to look at things, right? And go through the homework solutions. So, yeah. So have a good one, and we'll see you on Monday.